The Enigma Machine and Ultra, the Secret War of Codebreakers. In a Victorian mansion in the English countryside, hidden from public view and protected by layers of security, some of the war's most crucial battles were fought not with weapons, but with mathematics, logic, and brilliant minds working against time. Bletchley Park, located 50 miles north of London, was home to the Government Code and Cipher School, where British codebreakers waged war against German military communications encrypted by machines the Germans believed were unbreakable. The German Enigma machine, a sophisticated electromechanical encryption device, protected military communications with what appeared to be unbreakable ciphers. But British mathematicians, linguists, and engineers, working in conditions of absolute secrecy, found ways to break Enigma codes and read German messages. The intelligence produced, codenamed Ultra, gave Allied commanders insights into German plans and dispositions that many historians believe shortened the war by years and saved countless lives. This is the story of the secret war fought in code, where brilliance and determination defeated what the Germans believed was perfect security. The Enigma machine's origins predate World War II. Arthur Scherbius, a German engineer, invented the Enigma in the 1920s as a commercial encryption device for protecting business communications. The machine used rotating electrical rotors to scramble messages in ways that seemed impossibly complex to decipher. Each keystroke caused rotors to rotate, changing the encryption for the next letter, meaning the same letter encrypted differently each time it appeared. With multiple rotors and various settings, the number of possible encryption combinations was astronomical, over 150 quintillion possibilities on some versions. The German military, recognizing Enigma's potential, adopted modified versions for encrypting military communications. The Wehrmacht, Luftwaffe, and Kriegsmarine all used Enigma machines with different configurations and additional security features. The Germans believed Enigma was unbreakable. The mathematical complexity seemed to guarantee perfect security. This confidence led to widespread use. By World War II, tens of thousands of Enigma machines were in service throughout German military forces, encrypting vast amounts of tactical and strategic communications. The physical Enigma machine was relatively compact, about the size of a typewriter, housed in a wooden box for portability. It consisted of a keyboard for input, a lamp board showing the encrypted output, a plug board on military versions that added another layer of complexity, and the rotors that performed the actual encryption. Operators would set the rotors to specified starting positions, type the message, and record the letters that lit up on the lamp board. The encrypted message would be transmitted by radio, and the recipient, with an identical machine set to the same rotor positions, would type in the encrypted letters and read the decrypted message from the lamp board. The security of Enigma seemed perfect. Even if an enemy captured an Enigma machine, without knowing the rotor settings, which changed daily according to codebooks, the plugboard connections, and other configuration details, decryption would require testing astronomical numbers of possible settings, far beyond what seemed practically possible with 1940s technology. German cryptographers calculated that breaking Enigma would take thousands of years using conventional methods. This confidence was so strong that the Germans never seriously entertained the possibility that Enigma had been compromised. But they were wrong. Breaking Enigma became possible through a combination of factors: Polish mathematicians who made crucial early breakthroughs against Enigma, British brilliance and determination, captured code books and machines, German operational errors, and technology that automated the testing of millions of possible settings. The Polish contribution was foundational. In the 1930s, before the war, Polish cryptographers working for Polish military intelligence made the first breakthroughs against Enigma. Mathematicians Marian Rejewski, Jerzy Ruzicki, and Henryk Zygalski developed mathematical techniques for determining rotor wirings and exploited German operating procedures to reduce the number of possible settings that needed testing. They built electromechanical machines called bombas that automated the testing process. When Germany invaded Poland in September 1939, the Poles shared their knowledge with Britain and France, giving the Allies a crucial head start. The British Government Code and Cipher School moved to Bletchley Park in 1939, built on the Polish foundation. The operation grew from a handful of cryptographers to over 10,000 people by 1945, including mathematicians, linguists, engineers, and support staff. The scale and sophistication of the operation were unprecedented in intelligence history. The most famous figure at Bletchley Park was Alan Turing, a brilliant mathematician who would later be recognized as one of the fathers of computer science. Turing arrived at Bletchley in September 1939 and quickly made crucial contributions. He refined and expanded the Polish bomba concept, creating electromechanical machines called bombs that could test Enigma settings far faster than human operators. Turing's mathematical insights into Enigma's weaknesses and his ability to design machines that exploited those weaknesses were fundamental to British success. The bomb machines, named after the Polish devices but far more sophisticated, were the workhorses of Enigma codebreaking. Each bomb was a large cabinet filled with rotating drums, electrical connections, and switches. The machines simulated the action of multiple Enigma machines simultaneously, testing possible rotor settings at high speed. When a bomb found settings that produced sensible German text from encrypted messages, it would stop, and human cryptanalysts would verify and refine the settings. By 1945, Bletchley Park operated over 200 bombs capable of testing millions of Enigma configurations daily. Breaking Enigma required more than just machines. It required exploiting German mistakes and predictable habits. German operators, despite security procedures, often made errors that helped codebreakers. Some operators used predictable settings or sent routine messages with known content, nothing to report messages sent daily, weather reports following standard formats, etc. These cribs, portions of messages where the content could be guessed, gave codebreakers crucial starting points for determining daily settings. The human dimension of Bletchley Park operations was remarkable. The staff included some of Britain's finest minds, mathematicians from Cambridge and Oxford, linguists fluent in German, chess champions, crossword puzzle experts, and people with various specialized skills useful for cryptanalysis. They worked in shifts around the clock, in buildings heated inadequately in winter and stifling in summer, maintaining absolute secrecy about their work even to family members. Joan Clark, one of few female cryptanalysts at Bletchley Park and a close colleague of Alan Turing, described the environment. "We worked in huts, converted stable buildings, cold and drafty. The work was intensely mental, analyzing encrypted messages, looking for patterns, testing hypotheses. When we broke a message and revealed German plans, the satisfaction was enormous. But we couldn't celebrate openly or tell anyone outside our immediate colleagues. We lived in the world of complete secrecy, knowing our work was crucial but unable to share it with anyone." The intelligence derived from breaking Enigma, codenamed Ultra, proved invaluable across multiple theaters. In the Battle of the Atlantic, Ultra intelligence revealed U-boat positions and planned operations, allowing convoys to be routed away from submarine concentrations and enabling more effective anti-submarine warfare. This intelligence contribution to winning the Battle of the Atlantic was so significant that some historians argue it was the deciding factor. During the North African campaign, Ultra revealed German supply convoys' routes and schedules, allowing the Royal Navy and RAF to intercept them. Rommel's Africa Corps, starved of supplies due to these intercepts, was weakened significantly. Ultra also provided insights into German battle plans, allowing Allied commanders to position forces advantageously. The D-Day invasion benefited enormously. The deception operation, designed to convince Germans the invasion would come at Pas-de-Calais rather than Normandy, was verified as successful through ultra-intercepts showing German forces remained concentrated at Calais even after the Normandy landings began. Ultra also revealed German force dispositions, allowing Allied planners to avoid heavily defended areas and exploit weaknesses. The strategic value of Ultra created enormous security challenges. If Ultra intelligence was used too obviously, Germans might suspect their codes were compromised and change systems, ending the intelligence flow. A careful balance had to be maintained, using intelligence when it could appear to come from other sources, reconnaissance, conventional intelligence, etc., but not using it when use would be too obvious. Sometimes this meant allowing German attacks to succeed when stopping them would reveal code-breaking capability. The ethical dilemmas were profound. In November 1940, Ultra revealed that Luftwaffe bombers would attack Coventry. Churchill, aware of the impending attack, faced an impossible choice: warn Coventry and potentially compromise Ultra, or allow the attack to proceed, protecting the secret. He chose to protect Ultra. The bombing killed over 500 people and destroyed much of the city. Whether advance warning could have reduced casualties or whether evacuation would have revealed the intelligence source remains debated, but the decision illustrated the terrible calculus of intelligence in wartime. The operational use of Ultra required elaborate security procedures. Intelligence was distributed only to specifically cleared commanders and staff. Messages were hand-delivered by intelligence officers rather than transmitted by radio, where they might be intercepted. Cover stories were created to explain how intelligence was obtained: imaginary agents, supposed reconnaissance flights, fictional sources. The existence of Ultra was protected at all costs. Admiral Karl Dönitz, commanding German U-boat forces, suspected at times that U-boat positions were being compromised by intelligence rather than just by radar and direction finding. But German investigations repeatedly concluded that Enigma remained secure, and they attributed Allied successes to other factors. This confidence in Enigma's security, maintained despite mounting evidence that something was wrong, represented a critical German intelligence failure. The technical evolution at Bletchley Park went beyond Enigma breaking. British cryptanalysts also worked on other German codes and ciphers, including the Lorentz cipher used by German High Command for strategic communications. Breaking Lorentz required even more sophisticated technology, leading to development of Colossus, the world's first large-scale electronic computer. Colossus, designed by Tommy Flowers and operational from 1944, used thousands of vacuum tubes to perform logical operations at speeds impossible with mechanical systems. Colossus represented a technological leap that influenced post-war computer development. The scale of the Bletchley Park operation was staggering. At peak, over 10,000 people worked there, processing thousands of encrypted messages daily. The logistics of handling this volume, intercepting radio transmissions, transporting encrypted messages to Bletchley, analyzing them, distributing intelligence to commanders, required sophisticated organization. The operation ran 24 hours daily, with 3 shifts of cryptanalysts, machine operators, and support staff ensuring continuous operation. The secrecy surrounding Bletchley Park's work remained absolute not just during the war, but decades afterward. Personnel signed the Official Secrets Act and were forbidden from discussing their work. When the war ended and Bletchley Park was closed, equipment was destroyed, documents were burned, and personnel dispersed to other assignments without public recognition. The world knew nothing of Bletchley Park's contribution to victory. The secrecy only began lifting in the 1970s, when the British government declassified some Ultra materials. Even then, full disclosure took decades. Many Bletchley Park veterans died without ever being able to discuss their wartime service. Alan Turing, who committed suicide in 1954 after being prosecuted for homosexuality, never received public recognition for his wartime contributions. His pardon came only in 2013, nearly 60 years after his death. The strategic impact of Ultra has been extensively debated by historians.
Some argue it shortened the war by 2 years or more and saved hundreds of thousands of lives. Others suggest its impact, while significant, was one factor among many contributing to Allied victory. Quantifying intelligence impact is inherently difficult. How do you measure battles that didn't happen because intelligence allowed them to be avoided, or attacks that succeeded because intelligence revealed enemy weaknesses? What's clear is that Ultra provided Allied commanders with unprecedented insight into enemy intentions and capabilities. This advantage, carefully exploited while protecting its source, contributed significantly to Allied success across multiple theaters. The Battle of the Atlantic, the North African Campaign, the D-Day invasion, and numerous other operations benefited from Ultra intelligence. The German perspective reveals the costs of overconfidence in technical systems. German cryptographers and military leaders believed Enigma's mathematical complexity guaranteed security. This belief persisted despite warnings and evidence suggesting otherwise. The psychological inability to accept that their unbreakable code had been broken contributed to Germany's failure to protect their communications adequately. Post-war analysis showed that better German security procedures could have made Enigma much harder to break. If operators had followed proper procedures consistently, if messages had been shorter and less predictable, if certain technical modifications had been implemented, breaking Enigma would have been far more difficult or even impossible with wartime technology. But complacency born of overconfidence led to sloppy practices that cryptanalysts exploited. The technological legacy of Bletchley Park extended far beyond cryptanalysis. The bombs, and especially Colossus, pioneered computing technology. Alan Turing's theoretical work on computation, informed by his wartime experience, laid foundations for computer science. Many Bletchley Park veterans went on to careers in early computing, telecommunications, and technology, applying lessons learned during the war. The organizational lessons were equally important. Bletchley Park demonstrated that complex intellectual problems could be solved through interdisciplinary collaboration. Mathematicians working with linguists, engineers designing machines based on cryptanalyst specifications, logistics personnel ensuring smooth operation. This model of organized research towards specific goals influenced post-war scientific and intelligence organizations. The human cost of maintaining secrecy was significant, but often overlooked. Veterans who had made crucial contributions to victory couldn't discuss their service, couldn't explain gaps in their biographies, couldn't receive public recognition. Families knew their relatives had done something secret, but not what. The psychological burden of maintaining lifetime silence about significant accomplishments took its toll on many veterans. Mavis Beatty, a cryptanalyst who broke crucial Italian naval codes that contributed to British victories in the Mediterranean, described the cost. After the war, we couldn't tell anyone what we'd done. My husband knew I'd worked at Bletchley, but not what I did there. I met Bletchley colleagues at reunions where we could finally talk, but for decades I couldn't share with family or friends. It was like having a significant part of your life locked away in a box you couldn't open. The recognition that eventually came, decades late, was meaningful but bittersweet. Bletchley Park was preserved as a museum. Veterans were finally able to discuss their work publicly. Academic research revealed the full extent of Bletchley's contribution. But many veterans had died without recognition, and the delay in acknowledgement meant that many contributions remained underappreciated during veterans' lifetimes. Modern cryptography owes much to the Enigma story. The lessons learned that even sophisticated encryption can be broken through mathematical analysis and computing power, that operational security matters as much as technical security, that overconfidence in systems is dangerous, inform current cryptographic practice. The ongoing arms race between encryption and code breaking that characterized the Enigma story continues today with modern encryption algorithms and quantum computing. From Arthur Servius's commercial encryption device to German military adoption, from Polish mathematical breakthroughs to British industrial-scale code breaking, from Alan Turing's brilliant theoretical insights to the thousands of unnamed workers processing messages in cold Bletchley huts, from the ethical dilemmas of using intelligence while protecting sources to the decades of enforced silence afterward, The Enigma and Ultra story encompasses technological innovation, human brilliance, organizational achievement, and the profound impacts of intelligence in modern warfare. The secret war fought in code, invisible to those fighting visible battles, proved as crucial to victory as any campaign. The German belief in Enigma's invulnerability, proven false by Allied cryptanalysts, cost Germany the war-winning advantage of secure communications. The brilliant minds at Bletchley Park, working in obscurity and silence, made contributions to victory that went unrecognized for decades, but that historians now acknowledge as decisive. The codebreakers who defeated Enigma deserve recognition alongside the soldiers, sailors, and airmen who fought visible battles. Their weapons were mathematics and logic rather than guns and bombs, but their contribution to victory was no less significant.